Well, so dear colleagues, let us start our day session. And our first speaker is Anatolij Prykarpatsky from Krakow University of Technology, Poland, and also from Lviv Polytechnic University, Lviv. And this is a joint talk with Alexander Balinsky from Cardiff University of Great Britain. Anatolij Karolevich, прошу вас. Please.
Thank you very much to the organizer for the invitation to present my talk. And especially I would like to thank Sergei Maximenko for managing my scheduler of the report. So, what I'm going to present today, I will speak about classical problem of the Banach space theory, about the inclusion of some closed subspaces of the functional Banach space, like LP, into LQ, some Banach space with the number Q, which is greater. Such a problem has a lot of application in operator approximation theories and dynamical system theory also, and other applied fields. What I am about, speak in details. We can, for instance, recall classical result from Banach space theory, which were stated by Subramanian about inclusion theorems of LP into LQ for P less than Q, as well as I would like to mention here as my main topic of my talk, the classical Grothendieck theorem on the estimation of the dimension of a linear closed subspace embedded into LP, belonging to LP and embedded into L infinity with respect to probability measure mu on the space M. As well as one can recall the generalization of this classical theorem of Grothendieck on the case when we have a linear closed subspace belonging to the space of continuous function on the main space M, identically embedded into L2. This Grothendieck article was published in 1954 and is very important for many applications, as I mentioned before. And recently, in November 2025, the authors of the work authored by Li, Wu, and Xiong, entitled as the Grothendieck theorem in Bergkamp spaces, they studied and announced the result about the Grothendieck type embedding theorem for the Bergman spaces, AP, which is the space of holomorphic function on the some bounding domain omega, having some p integrable square degrees with respect to the Lebesgue measure on the set omega, bounded set omega. This, in part, they stated the following result theorem: let Q is greater than P and greater than 1, and for any bounded domain omega belonging to Cn complex and dimensional complex the space, a closed subspace SPQ belonging to AP, to our Bergman space, be identically embedded into Bergman space, AQ, for Q greater than P. Then the dimension of this subspace is less than infinity, is bounded. What is interesting, this type of theorem was already before stated for general Banach spaces LP on any space with measure probability measure mu in case, but for the specially chosen parameter parameter q greater than p. In this case, we have arbitrary parameter p q is which is greater than p is arbitrary, and the author of this article state that the dimension of this closed space of the Bargman space is bounded, yet they presented no estimation of this dimension. It is important because if you recall the classical Grothendieck theorem, the Grothendieck result holds an estimation of the dimension of this closed subspace of the Banach space LP. What we can add about this result of the Chinese authors. These authors based their proof on the following well-known classical theorem from functional analysis. Namely, the first result they used sounds as follows. If a bounded operator J from X to Y, from Banach space X to Banach space Y, is compact, and its image belonging to Y is closed, then dimension of this image is bounded. The second theorem, which was used by this author, is the classical Ries theorem, which sounds as follows: the linear subspace of any normal space X is locally compact if and only if it is finite dimensional. So we have the following problem. As the authors of the above theorem did not obtain the upper estimation of the dimension of this subspace belonging to the Bergman space AP, embedded into the Bergman space AP, we proposed a completely different approach to studying the Grothendieck embedding problem, and solved this problem once more using additional approach, and presented an upper estimation of the closed subspace dimension under regard. In particular, we have stated the following dimension estimation theorem. Let a linear closed subspace as belonging to Bergman space AP for any p greater than 1 be or equal than 1 be identically embedded into a Banach space AQ for q greater than p, where d lambda is the standard Lebesgue measure on bounded complex domains omega from the complex space Cn. Then the dimension dim as equal n is bounded, or the closed space proves to satisfy, being bounded, proves to satisfy the following equality: omega n squared and some numbers which will be explained a bit later, less than some bounded constant kpq greater than 0, where omega n, it is the volume of the compact unitary group SUN, module lambda is the volume of the bounded domain omega from Cn, and the constant Kn, depending on some vector xi0, is the corresponding homogeneity parameter at xi0 of the units belonging to the unit complex sphere in the complex space Cn. So we have exact and I guess it may be the best estimation of our of the dimension of this closed subspace embedded into the Bergman space, which can be obtained on the whole. So let's proceed to some points of this proof. Especially, I would like to mention on the new completely idea of proving the theorem, which is not based on the former mentioned compact theorem statement of the classical function analysis, yet is based on the completely other reasonings, which I would like to explain later. The first in the case when Q is equal to infinity, from our result we can reduce the obtained result about the estimation of the dimension of the subspace embedded into Bergman space, and we obtain the classical Grothendieck type theorem. We have a linear closed topological subspace SP embedded into AP Bergman space, being identically embedded into the Bergman space with respect to the Lebesgue measure on the bounded domain omega from the complex space. Then the dimension of this closed subspace proves to satisfy the exact inequality. The dimension is less than specially constructed constant Kp squared for some bounded constant. This constant and related with them another complex for the subspace embedded into Bergman space AQ for Q greater than P will be specified a bit below. Embedded of the closed subspace into Bergman space. So we start from the following result from function analysis about the Bergman spaces. In general, one can assume that this Bergman space can be replaced by any Banach spaces, yet we will not mention on this in detail. So we have the following theorem. The Bergman space AP with respect to Lebesgue measure the lambda unbounded domain omega are Banach spaces. This theorem is based on the local paracompactness of the complex bounded domain omega and the following classical Bergman estimation theorem. For any compact subset V belonging to omega and arbitrary function f from the Bergman space, there exists such a bounded constancy for which the supremum of the module of the function f is less than this constant multiplied by the norm of the function f, the p norm of the function f from the bounded space. A short sketch of this proof. As the norm of the function f from the Bergman space AP is a subharmonic function, then estimation like the formula 1 easily follows from the compactness of the subset V belonging to omega and the fact that the distance between closed space omega and the boundary of the omega is finite. So we can formulate our main dimension estimation theorem, which I skip. And now we can I can speak this repeated theorem, and now we proceed to construct the constants K, P, Q, which were mentioned before and which are used for estimation the dimension of the closed linear subspace in the Bergman space. We here consider a closed linear subspace SP from AP, which is embedded into AQ Banach space, and we consider the identical embedding mapping from AP to AQ. With take into account the corresponding norms. We have the following two lemmas, which we formulate as follows. Lemma 1, for any Q greater than P, there exists a bounded positive constant KPQ such that norm FQ less than KPQ constant multiplied by norma FP for any F from the subspace SP. Proof of the theorem is based on the fact that our mapping JPQ is closed map, and we can base our result taking into account the classical Banach's. So I here have shown that the mapping J is closed, and then you owing to the classical Banach closed graph theorem, we can construct the constant KPQ less than infinity, bounded K constant K, for which we have the following estimation of the norm Q and P. So we have constructed the constants KPQ, and next we need another lemma, which in part is the converse to the inequality 2, which was before mentioned. Sorry. So to constant to this one. So we have the following lemma. The lemma sounds as follows: there exists a bounded constant K with weight K, which is equal the following multiplication of constant K and C V before mentioned, such the following equality holds. So we have the norm F Q in this inclusion space, Bergman's space AQ, and the norm is estimated by the norm from the F2, from the Hilbert space A2, in the case when Q is equal to. So we have some kind of embedding of the Hilbert space A2 on the holomorphic function on the subset omega, and we have the additional estimation by the elements from the space AQ. So the proof of the theorem is based on some estimation of norm of the function f from the Bergman space AP, on which I skip. I will skip this proof, which is not instructive. Yet we proceed to the proving our main theorem. So, based on the lemmas above, one can proceed to proving our main theorem. First, we can observe that inequality which was before what just stated, so estimation by the Hilbert space subspace of function can be replaced by the following inequality using some classical Young inequality. So we have some functional L phi L phi on the space of function on the closed subspace SPQ, and we can estimate that this function, if to bound yourself by this function phi, some chosen function phi from the space related within the Young inequality. So we take the function phi from the SPQ and take it from the subspace SPQ where Q waved is satisfies the standard Young inequality reciprocal relationship with the parameter Q, and so, and the standard constraint phi norm of this function phi Q is taken to be equal to 1. It is necessary to say from the very beginning that the function phi is still not specified and it is taken arbitrary. Yet a bit later we will try to specify this function and we will choose it in the special form. So we have the following estimation owing to the statement in the inequality before. So, and we found that we reduced the problem of estimation of the dimension by means of the problem of choosing a special function phi from the Hilbert space A2 by Bergman space. In this case, will be Hilbert space belonging to subspace of belonging to our closed subspace SPQ, and we need to estimate this to find the estimation of this function phi in the case when it can be taken the best. So what about this function? We take any orthonormal basis in our subspace SPQ, closed subspace PQ, find a dimension of phi1 phi n for some n, bounded n, and we take it orthonormal. So we have norm is equal to 1, and we multiply this vector of function from the SPQ by any vector, complex vector A from Cn. So we have this usual scalar product, Euclidean scalar product in the complex space Cn, and we now we have the parameter, the function phi a parameterized by means of parameter a, and we can calculate that this norm phi a of this vector phi a is equal exactly the norm, the Euclidean norm of this parameter a n. So we now, if to take into account the equality before 11, so we need to calculate this norm of this vector un, and in the case under conditions that this norm is equal 1. So we see that the problem is reduced to estimate the norm of this vector. Yet the norm of this vector is exactly related with the norm of our function phi aq with respect to q waved in the following form. So we remember that our function phi a was taken to be to be such with norm 1. So, and here a is an arbitrary parameter. parameter from the Euclidean complex Euclidean space, and here we can show that this vector, this norm, is exactly can be calculated, and the norm is extracted from the integral, and we have the following conditions: that we have the vector, this norm is estimated by the norm of the vector A, Euclidean norm is in the power q, and some integral over the vector with respect to the measure de lambda, standard measure, Lebesgue measure, and this integral depends on the parameter psi belonging to the unit sphere in the complex space Cn. So we can reduce our problem to the estimation of the integral in the case when xi is not specified yet. But this estimation above is true for any parameter psi, for any parameter psi. So we proceed to the analysis of the integral above, and we can estimate this integral if to apply this averaging method, standard averaging method, over the unit boundary d, our unit sphere dn, which is equivalent to the double averaging over the compact Lie group SUN, as all vector xi of unit norm allow the representation xi is equal xi0 multiplied g, where g is element of our group SUN. And the vector xi0 can be taken arbitrary, but the most simple choice is to take it of the one in the following form 1 0 0, and whose norm is equal to 1, and so we now can average the left and right hand side of our integral. So we have the integration with respect to the standard invariant measure on the group SUN, compact Lie group SUN, the omega n, and we can obtain the following inequality. So we, as a result, we have the, and here we introduce the parameter kn depending on the xi0 vector from the complex space Cn. The standard homogeneity parameter when we extract the norm aq, the norm of the vector a in power q from the integral, and the omega n is the standard volume of our compact group SUN, and as a result we have the following estimation result, that the norm of our vector an is equal exactly omega n divided by the norm of the vector phi from the subspace SQ with respect to the norm q weight. So we can substitute this estimation of the vector A into our inequality, which was stated before, where we had the estimation of this norm by by the constant k weight pq, and as a result we obtained the following final inequality, that norm is equal exactly on this coefficient omega n divided by this norm, and we have the estimation. The following. So as a result, we have the estimation of the norm phi n. So we have in the denominator we have the norm of our model phi n. So our orthogonal orthonormal subset of function from the L from the Hilbert subspace A2 because we have and this norm should be calculated with respect to the norm q weight, which was reciprocal to the parameter q. Yet we can use the following inequality, the standard Young inequality, that this norm fq is less than the norm with respect to Hilbert norm A2 multiplied by the volume of our subset, our set omega in some power, and as a result we have the following estimation: that square root of n multiplied by the volume of the domain omega from our space Cn. Well, our main domain, complex domain. So the standard measure of the domain, volume of our domain omega. So if you substitute this norm into this inequality, which is exact inequality 16, so we obtain the following final numerical estimation for the dimension n of our subspace embedded into the Bergman space AQ. So we have the following constants: omega n multiplied by volume divided by n, and the homogeneity parameter kn squared multiplied by k weight squared. So the left-hand side is bounded from those integer n, which ensures the embedding subspace as our embedded closed subspace as from AP into Bergman space AQ for a given K and Q. To be finite dimensional, that is dimensions of this closed space SP equal n is less than infinity. So we have the numerical exact estimation, and from this formula, this estimation, we can obtain exactly exact value of this dimension n, for which this inequality is satisfied. So we have the standard result from the for estimation of the dimension from embedding from the theory of estimations closed subspace in some Banach spaces, and the estimation which can be considered, I guess, in some sense as the best estimation for the dimension. Regarding the critical case, when Q equals infinity, we can precede the following natural expression. We can consider the functional LXF, where LXF is the functional which assigns some value of the function f at some point x. So we have this function is a standard linear functional considered in the complex theory of Barman spaces, and we have the following estimation for its norm. We can, as we have the following embedding, we have the embedding here into the LAP2. So,
Анатолій Каролович, я
yes.
перепрошую, уже the time is over.
Yeah,
You
I
can say
have
a few
finished.
words.
I'm already finishing. So we can apply the standard reasoning about the estimation of this function, and we can obtain the following results. That this functional can be approximated by the orthonormal subset of function from our subspace SP, and as a result we can integrate this inequality with respect to the Lebesgue measure on the subset on the set omega, and we will find exactly the estimation of the dimension n, which exactly coincides with that which was before obtained by Grothendieck. Okay. So I have conclusion about our estimation results, as well. I have acknowledgement that this result were discussed with my colleagues Anatolij Prykarpatsky, and French mathematician Jean Pizier, for their instructive comments, remarks, and suggestions. And so we have the main references. Thank you very much for the present. Thank you, and for allowing to present the result and for attention.
Thank you very much, Senator.